something like this.
Okay. So you're trying to remove the singularity by adding that term. Is that enough? Because I mean, that only works in the limit where the sign presents it correctly.
No.
Works.
See, if S goes to prime, this is the only divergence. After I subtract this, I find a finite quantity, which actually I can compute. So I need to take the limit of this. I'll just put a -1/2, sorry. Okay, so, well, that's not very difficult to ask, but quickly mathematical ask to expand as the time goes to S. I mean, this is essentially 1/sinh squared. So there is a divergent part, and then there's a finite part, and there are positive powers of S minus S prime, which go to 0. So the answer is -1/24 L squared. So the stress tensor has a valve on the cylinder. What is the physical meaning of this? I could take the stress tensor, I could compute the energy as an integral or sigma of the sigma tau, for example. And if you do that, you'll find essentially the Casimir energy of a scalar field, of a free scalar on a sat. So this value here is intimately connected to the Casimir energy of the system. Now, in textbooks, very often they get the energy of the system just using some sort of a trick. They say, for example, they say, okay, this looks like an infinite power harmonic oscillator. Each harmonic oscillator gives me an energy which is n/2, and then we sum n/2, n equal to 1 to infinity, and we get -1/24. Okay. And then they involve the function regularization, analytic continuation, whatever. So there are reasons for which these tricks work, but there is a very precise physical meaning behind. Okay. The energy is something concrete. It's related to the stress tensor. If you regulate your stress tensor in a physical way, you're going to get a reasonable answer, physical answer for your energy. Using mathematical tricks works if you use the right one. And I mean, there are good reasons for which tricks that you see used in textbooks give the right answer. Would take probably too much time to discuss it, but pretty much they're all tricks whose purpose is to. Yes?
So the sum of the series, to obtain the sum of the series, you manipulate the oscillating series.
I don't do it like that. I did this. Okay. Now, what you sometimes see is things like this. You study this. This defines a nice analytic function of S for S smaller than -1, and then you analytically continue all the way to 1, and you call that the answer. That's a zeta function regularization.
You're adding position numbers.
I know, so this doesn't make sense. Okay. Now, what makes sense is to do some asymptotics. You can put the capital N here. And then you get something like, well, I guess you could probably do it, but, yeah. What was it? N+1. Let me see, I don't remember how you get the -1/24. Yeah, except that. Yeah. Yeah, I had to refresh my memory, but roughly. See. Yeah, of course. No, what is the point here? There is in the physical calculation, you're doing regularization, you pick some cutoff. Okay? So you don't send your momentum all the way to infinity. You pick some cutoff, so your sum is going to go up to momentum modes which have a certain size. But the size should be something physically defined, not something that depends on the size of your big circle. So if your cutoff is some lambda, you go to momentum which are up to something like L lambda. Okay? This has to be done correctly. I'm not doing it correctly. But the point is that you do this expansion, and now you see how they depend on this L and on lambda. You find something with positive powers of this L lambda. And then you find a constant term, which if you do things correctly should be -1/24, and then you get things that go to 0 as lambda goes to infinity. And then you say, oh, these things look like integrals. These are things that I can get rid of by some local counter term, by some local modification of my energy, of my stress tensor, whatever it is, integrated over the circle. And so you say, okay, in some way or another I get rid of them, and what you're left with is this constant. So this is a very, very fully explained. I'm sorry that I didn't put that details, but this is why these tricks based on zeta function regularization or things like that give you, at the end, if you do that properly, give you the right physical answer. It's because these tricks based on analytic continuation reproduce the constant part of some asymptotic expression, and then the polynomial part is removed by your regulator, can be removed by a regulator in the constant part. Anyway, we did like this. We got -1/24. We're happy. Yes.
So why do you not want our counter terms to depend on L?
Well, so it depends a bit what you want to do, but when you do quantum field theory, there's some notion of locality that you. I mean, one of the most powerful properties of quantum field theory is sort of the separation of scales, things that happen at some large scales do not depend on something that happens at small scales, or depend in a very limited So you don't want your short distance regulator to depend on what's going on far away. Now perhaps if this was an effective field theory, so if you had some other system like Atlantis at small scales, and then this is an effective description of it. So this regulator would sort of account for the difference in the definition of the Hamiltonian in the continuum and in the discrete system. And again, the difference is, it has to be the integral over the circle of something local. No, I didn't. So the documentation value of S is one way to compute the energy. Another way to compute the energy is just start from the original Hamiltonian that I did not write, which is something like sum of n, a minus n, or something like that. So sum of Hamiltonians of harmonic oscillators. And the 0-point energy of these harmonic oscillators. So, okay, so pretty much this was the reason I was keeping L until now, to show you why this subtraction is a reasonable thing to do. So from now on, I just have L to 1 and forget about L. Now you can already see that the integralization is going to give you some funny features when you try to when you try to do changes of coordinates, homomorphic changes of coordinates. Let me elaborate on it a little bit. Now, suppose you're studying some correlation function of just scalar fields. Okay. So this correlation function somewhere, doesn't matter where, cylinder, plane, some Riemann surface, I don't care. Because of this is just a Gaussian theory, this is given by some weak theorem, right? So you start doing weak contractions, you get some sums of products of 2-point functions. And these 2-point functions are just the gain function of the Laplacian operator. Crucially, this expression is pretty clearly called invariant under nice coordinate transformations. So if you do some coordinate transformations, you send your S to some S prime, which is a function of S. Then your scalar field, all that happens is in the Gaussian function of the scalar field is that the arguments of the scalar field change. So it means your scalar field is can be identified as X of S prime of S. Well, I guess you put some lines like this.
You're saying that you don't care about the manifold where you work on it, but still the green function would depend on that?
Yes, the green function will depend on that, but it's a function.
Right, okay, so
it means if I change coordinates, the function transforms as a function without any fancy behavior. You know, if I have X, the function is a square, I say that S is S prime cubed, then the function becomes S prime to the 6th. You plug the coordinate transformation inside the function. The first derivatives of your scalar field will transform like one forms. So there will be some Jacobian. Okay. So this is all pretty uncontroversial. Now what happens to the stress tensor? So this part transforms fine. So you get one of the Jacobian factors here, one here, no problem. But this part does not transform very nicely, right? So it means that if I try to understand how the tensor, the quantum stress tensor is related in some coordinate system or in some other coordinate system. So I will get something like this prime or S squared, which comes from this transformation. But I need to do something about that. So in a sense you get something like this. You get let me make sure that I'm too many primes. Let me call this new coordinate tilde. Okay, I'm sure I get the algebra a little bit wrong, but bear with me. Okay. I would like to say that I should get something like this. Well, I need a limit. S prime to S. I guess I'm there, still that over the S. There's still that prime over S prime. 1 over S tilde minus tilde prime squared minus 1 over S minus S squared. Oops. Now, the divergence of these two functions is actually the same. So the difference is finite. So defined, but it's not 0. So feel free to take this, expand it in powers of S prime minus S, and see what you get. You get some ugly looking expression. It's called the Schwarzian derivative of S tilde. So roughly you get something like this. Well, I just write it as changing your correlation function, or partition function when you change the metric. See, so if I change my metric by some delta H AB, the effect on partition function or correlation function should be the same as inserting an ATAB delta H AB inside. Now, if I try to write this in different coordinate systems, you know how the metric changes. It has some Jacobian, which is exactly the opposite of this. So this is fine, but this one is not. So you see that somehow you get some tension, some slight problem with coordinate changes of coordinates. Now, when I say changes of coordinates, these are really changes of coordinates together with the wild transformation, because here I did a calculation in some holomorphic, essentially with a flat metric, and I'm using in fact a change of coordinates and then a wild transformation to go back to flat metric. So this number here, also this term, it encodes part of the problems that this theory has with wild symmetry. So it's actually possible to argue that whatever classical theory which is classically by one part in terms of invariant is going to have points that look like this with some different number here called the central charge. So here, so discover that the scalar field has a problem of magnitude 1 with wild symmetry. Now this pops up in a lot of places, to see why we had to think about it better in some other lecture. The fact that here it's non-zero Cartesian energy is also tied into that. And there is another manifestation of this, which is the last thing I want to do today, naturally. Admittedly, we're a bit short on time, but so yeah, by the way, so this sort of expression over there, I could have also written as saying that T is minus 1/2 the naive normal ordering minus 1 over L squared. See, the naive normal order point function is something that especially by definition gives you 0 once you put it in the expectation value. And this minus 1 over 24 accounts for the difference. So if you actually expand the stress tensor in Fourier modes, let's something like this. Is convenient to denote it like this. So these are the Fourier modes of the stress tensor. As I mentioned up there, these Fourier modes actually they conserve charges of some symmetries. I'll leave the discussion of what symmetries those are for later, but they're actually coordinate transformations, complex coordinate transformations. All I wanted to do in the remaining 20 seconds is to compute the algebra satisfied by these modes. Okay. Now, you can do it directly from the definition, but there are some infinite sums that are a little bit bothersome. The nice way to do it is to first compute how these modes act on the operators, like stress tensor, like phi, like x, and then expand the operators in Fourier modes. Yes? Sorry, you're right. Normal order of an am is an am if